All right, segment 3 of chapter 7. We left off talking about wave functions, and I introduced Schrodinger's equation. So, wave functions brought about the next gentleman in our history series here, which is going to be Schrodinger. He gave solutions for the wave functions and energy levels of electrons. So what is a wave function then? It's a wave that corresponds to the electron. Okay, so we call them orbitals for the electrons in the atoms. It takes advantage of the amplitude, which is a wave function squared. It can be related to the probability of finding an electron at that given point. Okay, the nodes will be regions where electrons will not be found. So that means the orbitals then can be characterized by 3 quantum numbers. So the quantum numbers are going to be a shorthand way to describe the characteristics of the electron's positions. Now, the reason why we would do that is because then we're going to use that for bonding, and it's going to predict the behavior. So our first quantum number is n, the principal quantum number. All orbitals with the same n are in what's called the same shell. Okay, so if n equals 1, then all the electrons that are there will all be in the same shell. Then there's L. L is the secondary quantum number. This divides the shells into smaller groups called subshells. Next is M sub L. This is the magnetic quantum number, and it divides the subshells into individual orbitals. So again, n is the principal quantum number. For n, your values are allowed to be positive integers, only positive integers, from 1 to infinity. Now in the reality, when we're looking at real atoms, we don't need to go past 7. Okay, so n can equal 1, 2, 3, 4, 5, all the way to infinity. And actually in real atoms, we don't go past 4. Okay. This is going to determine the size of the orbital, the total energy of the orbital. Okay, so R sub HC is equal to 2.18 times 10 to the negative 18 joules per atom. And so we see that divided by n squared, right? So for a given atom then, the lower the n equals the lower the energy, okay? The more negative, which means the more stable. So if you have a small n, then we have a more stable energy level. Now, L is the orbital angular momentum. Now, its values are going to be 0 through a whole integer, right? Because it's going to be n minus 1. So n can go to infinity, but L can only go up to n minus 1. We represent those by letters, and here's where you're going to start to see some similarity with what you remember, hopefully. So if you remember your electron configurations, these are going to be your S, your P, your D, your F. And that's why we stop at 4, right? And then there's G, H, so forth and so on. So we'll give a letter designation as well. The orbital designation would be number and then letter, so NL, right? So the 3S, the 5P, 2, well, you can't have D, but 5D, 3P. All right, possible values of L will depend on N. So N different values of L for any given N. This is going to determine the shape of the orbital. Next we have M sub L, which is the magnetic quantum number. And here your values are allowed to be negative L to 0 and then to plus L. So an example, when L equals 2, M sub L can then be negative 2, negative 1, 0, plus 1, plus 2. Now, possible values of ML then depend on L. There are 2L plus 1 different values of ML for a given L. Okay, so you might have to make some mental sense of that. So basically we're saying if L equals 2, then you get 2 times 2 plus 1, or 5 different orbitals in that space. Okay, so it's going to determine the orientation of those space. To designate specific orbital, you need 3 different quantum numbers. You need the N, you need the L, and you know the M sub L. And again, if you've ever done electron configurations, that's what this is going to develop. So if you remember with electron configurations, you had to have an energy level, that's actually N. You had to have an orbital, that's L. And then how many electrons were in there. Remember the maximums. So like a P can hold up to 6. Okay. The summary of the relationships among the quantum numbers. So if N is equal to 1, then L has to be 0, and the only ML would be 0. So think about that. If we have the 1s, right? The s can only hold 2 electrons. There's only one shape. So that means we on the first energy level, we have one orbital. It's got one shape. Now we go to the second energy level. When n equals 2, now for our values of L, we could have 0 or we could have 1. Now when it's 0, because it's two different cases, when L is 0, that means ML has to be 0. That means the shape is an S. Okay, so value of ML is 0, shape is S. Or it could be a 1. If L is 1, M sub L could be -1, 0, or 1. That's a P. So if you understand electron configurations already, those electron configurations are based on these quantum numbers. We took out all the detail to explain electron configurations, and we looked at it as a pattern. If you've never seen electron configurations before, then these words make no sense to you, but we're going to cover those shortly. Okay. Now, orbitals of many of electrons. So again, the 1s down here, it's going to be the lowest in energy. Remember, the smaller the n, the more stable that orbital is going to be, that energy level. So it's the lowest in energy. N has to equal 1, L has to equal 0, M sub L has to equal 0. In the second energy level, we can have 2s, then we know L equals 0, ML equals 0. Or we could have 2p. If that's the case, then L could equal 1, M sub L could be -1, 0, or +1. And we could do this for each one of these, and we could break it apart just like that. That would be your orbital designation. And of course, it's based on the first two quantum numbers, the number for N and the letter for L. Now, how many electrons can go into each orbital? Hopefully we already recognize 2 electrons. That was the need for the other quantum number. Now for the quantum number, M sub s, we have the spin. It can spin left or it can spin right. So this is going to arise out of the behavior of electron in a magnetic field. So remember, the electron has a negative charge. So it's going to act like a top when I put it in a magnetic field. The spinning charge is just like a magnet itself. So if it's spinning left, it's got a momentum, an angular momentum going one direction. If it's spinning right, it's got it in another direction. So the electron then is going to behave like a magnet. This leads to two possible directions of electron spin. Up and of course down. Okay? North and south if you want. So that means M sub s can be +1/2 or -1/2. That's how we designate it. So M sub s could be +1/2 or -1/2. Now, because of the spin, what comes out of this is called the Pauli Exclusion Principle. Now, you might have seen this if you've looked at electron configurations. No two electrons in the same atom can have the same set of all 4 quantum numbers. Okay? You can't have it. So if I have 50,000 electrons, none of them can have the same 4 letters, same 4 designations. Okay? Something's got to be different about each one. You can only have 2 electrons per orbital. So 2 of them get close, so they could have the same N, L, and ML, but then the MS has to be +1/2 or -1/2. So 2 electrons in the same orbital then must have opposite spin. And so the electrons are said to be paired. Now, we know this from magnetic properties. 2 electrons in the same orbital have different spins. We represent those with arrows. One pointing up, one pointing down. Doesn't matter which is which. If the spins are paired, we call that dimagnetic. Okay, that means the sample itself is not going to be attracted to a magnetic field. Magnetic effects then tend to cancel each other out. Now, if I have two electrons in different orbitals with the same spin, the spins are termed to be unpaired, and they are called what's paramagnetic. At this point, that sample should be attracted to a magnetic field. The more unpaired electrons lead to a stronger attraction to a magnet. Okay? And we can actually measure the extent of attraction. That's going to give given the number of unpaired spins, right? So the number of orbitals and electrons in the orbitals. So S can only have one orbital, can hold a maximum of 2 electrons. P, 3 orbitals, right? Because it's -1, 0, +1. 6 total electrons. D would be 5, 10 electrons. F would be 7, 14 electrons. Now for your shells, this would be 1, 2, 3, or 4, right? So 1, you get 1s subshell. Maximum shell population would be 2. For the second shell, you're going to have an S and a P. That's going to give us a total of 8 electrons. For the third shell, you're going to have an S, a P, and a D. This is a typo here. They need to fix this. This is 2S. That'd be awfully confusing. You have 18 electrons. In the 4S, in the fourth shell, we can have the 4S, the 4P, the 4D, the 4F. Total of 32 electrons. So if you've ever looked at electron configurations, hopefully that makes quite a bit of sense here. If not, then hopefully once we do electron configurations, which will be coming up soon, that'll make better sense. All right, so your turn. Which of the following is a valid set of 4 quantum numbers? N, L, M sub L, and M sub S. Okay, hopefully right away you realize you can eliminate B, right? Because remember, MS has to be +1/2 or -1/2. So let's see. The answer here is going to be C, right? A, we could have N equals 3, L could equal 2. That's good. But M sub L can't be 3, right? Because M sub L could be -2, -1, 0, 1, or 2. All right. D, we have N equals 3. And then L, remember, can only be up to N minus 1. So L cannot be the same number as N. And then for E, N cannot equal 0. Right? It has to be +1 up. Okay, integer. All right, what is the maximum number of electrons allowed in a set of 4p orbitals? Okay, in a set of 4p orbitals. Now remember, you can use your electron configurations for this. The p is what's going to be important here. P, we know, represents M sub L of 1. That's going to be -1, 0, +1. Each one of those can hold 2 electrons. That gives us a total of 6 electrons. All right, determine the number of electrons in an atom that can have a principal quantum number of 3 and list the possible subshells they occupy. Okay, determine the number of electrons in an atom that can have a principal quantum number of 3. So N is going to equal 3. And list the possible subshells they occupy. And hopefully you've got A, 18, where we have a 3S, a 3P, and a 3D. All right, so ground state electron arrangements. Okay, so ground state electron arrangements. Again, this is just the electron configurations. So if you've ever seen these before, this might be, old hat type stuff. But if you've not seen them before, we're going to go through it like you've never seen it before, then bear with it, all right? So distribution of electrons among the orbitals of an atom. So we want to list the subshells that contain electrons. So basically, if we're going to step back just a smidge and look at this, what we're concerned about are where are the electrons, right? So we know that in chemistry, when it comes to reactions, bonding, all these things, everything comes down to the energetics of where the electrons are actually located. So we want to know basically where are all the electrons. we're going to indicate the electron population with a superscript. Okay, so for instance, nitrogen then is going to be 1s2, 2s2, 2p3. From there, we can draw out orbital diagrams, and this is a way to represent the electrons in the orbitals. And they're going to represent each orbital with a circle or a line. Okay, so we're going to use arrows to indicate spin of each electron. So in other words, we're going to say here's nitrogen. And nitrogen in the 1s can hold 2 electrons, one spinning up, one spinning down. Then it has a 2s, one spinning up, one spinning down. Then when it gets to 2p, we can see we have all 3 of them rolling paramagnetic there. They're unpaired, and they're all spinning up. Now, in reality, they could be spinning up, down, down. They could be spinning down, down, down. They could be up, down, up. Any combination. Okay, we don't know. Now, when we look at an energy level diagram for multi-electrons, what we're looking at is how to put the electrons into the diagram. So we're going to have some rules. The first rule is going to be the Anbau Principle. So this is going to be our energy diagram. Notice it's keeping track of all the orbitals for us. We have the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 6s. And of course, these would just keep going. So it'd be a 5d, a 5f, a 6p, a 6d, a 6f. Then we'd have the 7s, so forth and so on, all the way up. It would just keep going. Now, the Anbau Principle is German for build up. We're going to build it up, okay? We're going to have the Pauli Exclusion Principle, which means that's how we're going to have our ms, all right? M sub s told us plus 1/2, minus 1/2. That means 2 electrons per orbital. We're going to fill the following the order suggested by the periodic table. So if you're looking at a periodic table and trying to do electron configurations, what you're going to notice is the first 2 columns on the periodic table are going to be called the S block. Then right after that is the middle of the transition metals. That's going to be your D block. Then next to the D block will be the very end, which will be the P block. And then down at the bottom, you have 2 rows. We call that the F block. Okay. Whenever you're in that block, that's the orbital you should be in. Now, your spins must be paired. Okay, so we're going to fill them up, and we're going to fill them as we go. Now, Hunds Rule comes in and says, if you have more than one orbital all at the same energy, right, so like a p orbital, then what we're going to do is we're going to put 1 electron into each orbital with spins parallel all up until all are half filled. Then after the orbitals are going to be half full, we'll start to pair the electrons up. Now, why is it we do that? Well, remember, there's going to be some repulsion of electrons in the same region of space. So if they can have their own little compartment, that's what they're going to do. They're going to take their own space. They're not going to share space until they have to. Once they start to share, they will have to be plus 1/2, minus 1/2. Okay. So here's our orbital diagram for electron configurations where nitrogen has a Z equaling 7. Z is just the charge. We have 7 electrons. Each arrow is going to represent 1 electron. So the first thing I'm going to do is put 2 electrons in the 1s. 1 spinning up, 1 spinning down. Then I'm going to put in 2 more electrons into the 2s. 1 spinning up, 1 spinning down. Now notice there's a difference in energy. Now once we get to the 2p, they're all the same energy, so I'm going to put 1 into each one. Now when I go to present the electron configuration, I'm going to base it off this chart. Okay, so we're going to have 1s, and then we have a 2. Okay, so that's going to be 1s, and it's got 2 electrons. So we're going to note that as a superscript. Then we have the 2s. So we have 2s, and it's got 2 electrons. Then we started filling the 2p. It's going to be 2p. But now I only have 1, 2, 3. So that's going to be 2p, 3. Now, once I've got the orbitals all figured out, I just list them straight across. 1s2, 2s2, 2p3. Now note because we have unpaired electrons, this means that nitrogen is actually paramagnetic and should be attracted to a magnetic field. All right, so let's try something a little more difficult here. Let's look at vanadium. vanadium, we have 23 total electrons. So each arrow again will represent an electron. We're going to put 2 in the 1s, 2 in the 2s. Now we're going to fill that 2p, so it's going to end up with 6. Then 2 in the 3s. We're going to fill that 3p, then the 4s, and then the 3d. Now notice that we did the 4s and then the 3d. Well, keep in mind, that's where our periodic table is going to help us. Okay, so once we start to get higher up in energy levels, we get what's called overlapping, where some of the, like the 3D now, is actually higher in energy than the 4s. So we'll fill the 4s. Now another thing that's going on here that you got to be aware of is that as I fill up the orbitals, they actually move in energy. So even though on my piece of paper here on the slide it's fixed, that's not what's happening. The minute I put an electron in it, the energy level is going to change one way or another. Okay? In some cases it might go up, most cases it goes down in energy. When I start to pair them up, we're going to see a flux in energy. Okay, so when we start to do those types of things, and we're going to learn some other little tactics or techniques that the electrons will do, it's going to change things up a bit. So as the atom gets more complicated, more of those nuances, I guess we'll call them, take place. Okay. Now, if I'm just going to read this directly, just like we did before, we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then finally 3d3. Okay. And once again, we have unpaired electrons, which means vanadium should be paramagnetic. All right, give electron configurations and orbital diagrams for Na and As and determine if they are para or diamagnetic. Okay, so here's our chart. Now remember for sodium, Z equals 11. So give you a few seconds here. All right, so hopefully you put 2 in the 1s, then you put 2 in the 2s, then you put 6 in the 2p, and then 1 in the 3s. We have one unpaired electron, and so we would expect sodium to be paramagnetic. Okay, so far so good. All right, now we'll look at arsenic. 33. So again, we're going to put 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p. We now have 2 electrons in the 3s. We'll have 6 in the 3p, 2 in the 4s, all 10 in the 3d. Might have to count our electrons right now. That gives us what? 2, 4, that's 10, 12, 18, 19, 20, 30, which means we have 3 more left over. And so there they are in the 4p. Also unpaired, which means arsenic should also be paramagnetic. All right. What is the correct ground state electron configuration for silicon? So again, you might want to pause it here, work your way through it. If you've got a periodic table in front of you, you know you have to end in the third period, which is going to be the third energy level. You're going to be over there underneath carbon, which is in the P block. So it's going to be 3P. And it's the second one in. And so it's going to be 1s2, 2s2, 2p6, 3s2, 3p2. All right. Is ruthenium diamagnetic or paramagnetic? And if paramagnetic, how many unpaired electrons does it have? So again, I'll pause. I want to get your periodic table out, make a quick sketch of an electron diagram if you want. And hopefully you come up with paramagnetic with 4 electrons. So you end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d6. And then when we write it all out, we get into that D, we have 5 spaces, and so we get 1 pair and then 4 of them individual. Okay. Again, the more electron configurations you practice, the more quantum numbers you practice, the easier it will get. Again, when you're looking at the periodic table, remember you can divide it into 2, 10, 6, and 14 columns. Notice for the S, if we put in that first energy level, we have helium here, and we have hydrogen over here. Whenever I think in terms of electrons or electron configurations, I usually, in my mind, just move that helium over here. Okay, it just makes life a little easier sometimes. So you're going to divide this into regions of 2, 6, 10, and 14 columns. This equals the maximum number of electrons in the SP, D, and F sublevels. Okay, so sublevels in the periodic table. So you have the 1s has to be hydrogen and helium. Then we have the 2s, 2p, 3s, 3p, 4s, 3d. Okay, so you can just follow along with that if you want. The sublevels of the periodic table, each row represents a different energy level, and then of course each region of the chart represents a different type of sublevel. All right, so we're going to stop the segment here. We're 25 minutes in, and next we're going to look at being ready to put electrons into atoms. And so we're going to get more into the electron configurations of things. All right, so stay tuned for that.